Hi and welcome. My name is Bob Deibner, Senior Applications Engineer at Corellis. In this presentation, I'll be showcasing ScanExpress TPG software, which provides a highly advanced automated boundary scan test design environment, perfect for quick and efficient creation of complete boundary scan tests for all IEEE 1149.1 and .6 compliant systems. Let's get started. Software demonstration of ScanExpress TPG. So to do that, I am first going to launch ScanExpress TPG. I can do that from my Start menu. I also have icons on the desktop, but we'll use the Start menu. ScanExpress TPG. Everything is under the ScanExpress folder. There we go. And although we are not going to use the demo board for this, we're doing development. I'm going to go ahead and have this picture up for you. It'll give you an idea of what we are dealing with when we're developing. This is the board that I am going to be developing a test procedure for. So for ScanExpress TPG, we start by creating a project. I can click Create New Project. Let's give it a name. This board is called Scan Plus Demo Board. We can give it an identifier. This is not required, but I like to use my revision as an identifier. So if I type revd there, it's also going to append that to my suggested file name. You can customize this later if you'd like to override it. Description, this is just for you. So Scan Plus Demo Board revd test procedure. If I had an existing file that I was basing this on, for example, this is a new rev of an existing test procedure, I can use this based on option to specify that I'm going to start not from scratch, but from an existing procedure. Number one, we need to specify our netlist, so I click Browse. When you install Corellis ScanExpress software, we create this Corellis examples directory on your C drive. I'm going to be using these examples as part of my demonstration. So I'm going to start in the ScanExpress TPG directory, Scan Plus Demo Board, and I have a netlist right here. I specified my Telesys netlist. If it's not Telesys format, it'll be automatically converted. If it is not a supported format, then the software will let me know that it's unsupported. For my bill of materials, I have an Excel file. I click Select. Bill of materials can be either XLS, so Excel, or comma separated values, CSV file. My schematic file is in PDF. Before I open it, I'm going to go ahead and right click and open it with my Adobe Reader as well so that we can see it. This is a PDF schematic. It is searchable. So if I hit Control F and I type something in, I can search through it, which also means that our software can use the API that Adobe provides for this software to control it and search for things for you. This is the block diagram of our system. We have 5 boundary scan devices. So you can see test data in on the left-hand side to test data out on the right-hand side. We also have some non-boundary scan devices that are connected to these. So for example, we can use our PowerPC to access SDRAM U9 and U10 so that we can indirectly test those. Similarly, we can access U12 with our PowerPC and U11 with our Lattice CPLD, and our SSRAM is connected to one of our devices and FPGA. I'm going to minimize that and leave it open for now. While right now, for the purposes of presentation, I'm using 1080p. This is actually a 4K monitor, but I'm using the 1080p mode for presentation purposes. We do find a lot of desktop space does help, because then you can have both the software up and any documentation you need, like a PDF schematic, like a bill of materials or instructions. So those are the 3 files I needed to specify up front: netlist, bill of materials, and schematic PDF. If I have a was-is file, for example, if I'm starting from another project, we went through layout and I didn't back annotate my reference designators, so they're now new reference designators. I may need a was-is file to tell me what those new ones are, so that it does not need me to identify new models. If I click create, it will create my project. It's telling me it doesn't exist yet. That's fine, I'm gonna create it. And next step, specify my bill of materials columns. In my bill of materials, reference designator is column E, so I can specify E. I can also right click and choose it from the column. So ref des is E, part number is B, and part description is C. I click OK. It processes my net list, determines it was an Allegro type net list, converted it to Telesys, and we're now ready to load it. So with this project management interface, it'll show you the available projects within your upper level project. So we have the PRJ file, which references multiple TPP files. The TPP you can think of, that's a test preparation project. You're going to have one TPP per test procedure, like you can call that a revision of a UUT. When I say UUT, that is unit under test. So we can think like maybe I have a new board coming out, then I would make a new TPP to describe that board. And then that TPP results in test steps that we can execute. If I want to compare a new test procedure against an old one, we have a comparison utility here just for that. If you want to add additional test procedures to an upper level project, you can do that. But for now, I can either double click this or click open. It will process the files. It's warning me that I have some switches that were in the bill of materials, but not in the net list. That is intentional. We have fault switches on the board that are not included in the net list, but are included in the bill of materials. One major advantage of having a bill of materials, and specifically an assembly BOM, an assembly bill of materials, is that it will tell us when a part is not installed. So if it does not find a part in the bill of materials, it will mark it as not underscore installed, which tells us do not model that device, it's not populated. If I click OK, it loads my project into the preparation phase. So notice that we've passed the netlist step. That was taken care of by the project interface. If we started here, we could have specified these manually instead of going through the project creation interface. There's multiple ways to do things. You will find with our software, in some cases, it is strongly opinionated software, meaning there's one way to do things. But in many cases, we prefer to give you options. So there's more than one way to do many operations, and really it comes down to preference. We have some customers who have been using the software for a very long time. They don't need the project interface. They manage it themselves, so they can go straight to preparation. And if you are doing that consistently, you can also set up command line switches to go straight to project preparation or generation. So we are now at the BSDL file screen. Notice that all of these buttons can be clicked now, so I can go to any of these pages, but there's meaning to the order. If I've not specified BSDL files yet, then it will not be able to determine differential termination resistors. If I haven't specified power and ground, it will not be able to determine what is a pull up and a pull down. If I haven't specified my resistors and transparents, we won't be able to automatically order the scan chain, and so on. So every step builds on the last. Each of these pages has a most relevant filter that can be switched to all devices to show everything, or just most relevant based on pattern matching. I can also filter it just by typing in what I'd like to filter. So in this case, I'm filtering on U1. If this is too small, please let me know and I can use the magnifier as well. But it should be at an okay resolution for most people to be able to see what I'm doing. So if I change this device filter back to most relevant, I see 5 devices. These are my boundary scan devices. I have some options for finding BSDL files. In this case, I've already done the work, or really somebody else has done it for me, of going to the vendor site, going to the Altera site, downloading the 7032 BTC44 BSDL, the Spartan 2 for Xilinx, the Lattice CPLD, the PowerPC 405, and the Xilinx Cool Runner. All of these BSDLs have already been downloaded and collected in the Corellis examples directory. So if I open this up and I go to see Corellis examples, ScanExpress TPG, Scan Plus Demo Board, I already have these BSDL files in this folder ready to go, which means I can try to auto find. It'll use pattern matching to look for BSDL files that match. In this case, it actually found them in my embedded library, but it also searches both your program data, Corellis libraries, and your project directory, which is this directory. So right now, we have a list of our boundary scan devices. We have the BSDLs associated with them, the package, and whether or not they support the IEEE 1149.6 standard. If we find that it supports the 1149.6 standard based on the BSDL, we will turn that on and we will put a yes in that column to indicate to you that yes, we are going to use that capability. Originally, when we implemented 1149.6, it was completely transparent. We will use it and turn on that capability whenever it's available. But we had customers who said, we'd like to see that it's going to turn it on. So we added that to show you when you do have capable components. TPG and grab another BSDL. I can have multiple BSDLs associated with one part. The order is important, so I can move up and move down or drag and drop. And then once I have all of the BSDLs for the single device, I click OK, and it now adds multiple BSDLs just for that one part. Now in this case, I just want a single BSDL, so I'm going to go back and select. So the BSDL describes what these devices do. If I double click, it'll open it in a text editor. Now I know this is going to be hard to see, so let's grab that magnifier again. So this BSDL is for entity EPM 7032 BT44. It has port entries that describe the ports available to us. Pin map tells us how those ports map to actual physical pins. Our JTAG signals are defined. Our instructions are defined. So it tells us the instruction register length is 10. The opcodes available to us are bypass, XTest, sample, ID code, user code, and clamp. So all of those are well defined by the standard, no custom registers or no custom instructions that they're using. IR capture code is specified here. That's a fixed code that we will be able to sample. ID code register. So version, part number, manufacturer, and then last bit is always 1. User code can be customizable. This is a CPLD, so more than likely with the Altera software, you could program that user code to be something else. Then you would go and update the BSDL to reflect that. Otherwise, it is don't care or X. And finally, our boundary scan register is defined as cells. You can see this first one, this first set of cells, input and then 2 internals, input and then 2 internals. And then here we have some bidirectional capabilities where we have input control and an output 3 being tristatable output. So I'm not going to go into too much detail on BSDLs, but I just wanted to show you that very quickly to see what we're reading in here. This gives us information about how the parts work. If I had a hierarchical device like a JTAG bridge, like the Firecron JTS06BU or Texas Instruments 8997 or 96, then I could specify that here. And that will tell the software that there's a bridge that it needs to operate, and these devices are behind that JTAG bridge. One aside for AutoFind. Our software has AutoFind on each of these pages. That is a combination of just general pattern matching and also automation configuration. This is customizable. Let me pin this to my start or my taskbar so that I can just pull it up when I need it. There we go. So in this case, we are looking for nets named 0V or 0_V, common, chassis, ground, or if they contain GND, that's what we're going to look for when we're looking for ground net names. So we're using these pattern matching strings to figure out what we expect to be power or ground. And the same thing applies to device naming. So if we see R followed by a number, that's going to be a resistor. These are all customizable. So if instead of using U followed by a number, you can use IC followed by a number or something similar. depending on your organization's convention for reference designators. So over time, you can add to this. These are the defaults that we provide to you. And over time, let's close that. We can also build up a database of part number to model matching. So in this case, I've done some demos. I've worked on some other boards at this station. So my part numbers have been updating over time. As I associate models, for example, as I associated this, let's see, what is that? VU, so that's Vertex Ultrascale from Xilinx. When I did some development with that, it learned that the part number that I have here, and that's based on our BOM convention, you know, the part number is not always exactly the same, will map to this BSDL file. The BSDL file also gets saved on the station so that it can be pulled out later. This can be saved, moved to other stations. You can load an existing database if you already have one. And over time, as you use the software, that will get better. It will learn more about what parts map to which device models. So I now have my BSDLs. So once we've specified our BSDL files, we click Next. We are now at the power and ground screen. The auto find function will look at your net names and determine which ones it thinks are ground and power. And if I sort by power and ground, it'll show me which ones it associated. So I have 5 volts, 3.3 volts, 2.5 volts, ground, and AVDD. So I can show you how the view schematic function works here. So I have AVDD. If I right click, choose view schematic. It found 2 instances. So here's instance number 1. So I have, and we should be able to zoom in on this, 2.5 volts goes through a 10 ohm resistor to this net AVDD. So 10 ohms is pretty strong. That's very little resistance. So for all intents and purposes, AVDD is a reference voltage. In fact, it's probably used as something like that in the PowerPC. So what I can do is go ahead and leave that as power. Now, if I found that that was not a reference voltage, if maybe it was 0.9 volts and I don't have 0.9 volt logic on my board, then I would specify non-digital. This 5 volt pin, we do recommend that if you're using 3.3 volt logic, it's not incredibly uncommon for a 3.3 volt logic device to be pulled up to 5 volts. So you can just leave 5 volts as power. It would be if I had good compelling reason that I don't want this 5 volt to ever be considered a digital logic high, I can click non-digital. That will tell our software, do not try to use this as a pull-up voltage. It is unreliable. But in this case, I'm going to use power. One last thing that I probably should have made the first thing is when by default, we will sort this by pins per net. In this case, ground and power are almost always going to be your highest pin count nets. So we do recommend sort by pins per net, take a look at these. That'll be a good indicator of your powers and ground. You may have some power voltage references that don't go to many different nets, but that's the rarer case. If I click next, I'm now on resistors. So I mentioned that our pattern matching will look for R followed by a number by default. So if I go auto find, it's going to prompt me to choose a transparent model library file. We provide one of these to you, or you can always use your own. If you do a lot of development, you can maintain your own and bring it from one project to the next. But for me, I'm going to use the default library. It auto found my resistors. Let's see, so I have some pull-ups, series, pull-up, pull down. Notice that it classified these automatically. That is based on the power and ground nets that they are connected to. So if we find that a resistor connects to 3.3 volts, we will call it a pull-up. We have this option specifically for very, very large projects where we found that our classification algorithm, it's going to struggle when you have just a whole bunch of resistors, because it does have to traverse through multiple paths. For example, you could have 2 series resistors and then a pull-up. So because of that, we have this option to turn off real-time classification. Most people are not going to need that. If you do find this is very sluggish when you make a change, then you can turn that off, and then you'll only reclassify when you click that Update Now button. If you have a resistor that is non-testable, we have this non-testable button. In this case, I'm going to assume all of my resistors are testable. Let's see, so I have some 33 ohm resistors. The software classified them as series. That's good, but because it was in the slides, I would like to treat those as low impedance. So I'm going to remove the model, and I'm going to treat them as transparent on the next step. So let's see what else I have. I have some 100 ohm resistors. Those I'm going to treat as transparent. My 10 ohm right here, we're going to call that transparent, so I'll remove it for now. 33. So the only thing I have left here are my resistor networks. When you associate models, you can tell the software to associate a model with all devices that have that part number. So I can choose right-click resistor network for all. But before I do that, I want to right-click and view schematic so that I can see what this resistor network looks like. Let's zoom in on that. I'll try to get everything on the same screen. So I have RN1, 2, 4, and 5 all have the same part. So I can right-click resistor network for all, and let's see what I have. This is a 16-pin resistor network. So I can choose resistor dash network 16. Is it bus? This is not bus. This is parallel, so 16 parallel. One thing I do recommend when you are using our software, anytime you associate a transparent model, before you commit to it, click View, compare it against your schematic symbol. Make sure you have the right pin out. That is one of the most common mistakes, is to choose a model that's not the same pin out as what we're looking at in the schematic. So pin 1 connects to 16, 2 to 15, 3 to 14, and so on. This model looks correct for this device. I'm going to click OK, and it associated it with all of those. Now there's something a little weird going on there where I see series and pull-up. You know what? I picked the wrong model. This is a bus, not parallel. So if I go resistor network, choose bus, that's what I get for not actually paying attention when I'm speaking. Pin 1 through resistance to 16, 2 to 16, 3 to 16. Click OK, click OK. There we go, that's the right model. This is actually acting as a pull-up. We have one more. This is RN3. It looks like a 1K resistor network. I know that it's on the same page, so I can just scroll down to it. I like to point something out here it's mostly for the newer test engineers and those who are relatively new to industry. In this case, my schematic says 4.7K, but my bill of materials says 1K. Who do you believe first? In general, you're going to believe your assembly BOM. Your assembly BOM is going to essentially be telling all of your machines, right, the pick and place machine and things like that, and the people feeding those, this is what you're going to put there. So ideally, your assembly BOM is the most reliable source of information outside of your own eyes looking at a board. So for example, I think this, it's not on this board on the top, it's actually on the back, so I can't show it to you. But I could, for example, use my eyes to find that resistor pack and make sure it's the correct one. So rule of thumb is schematic is least reliable, bill of materials is more reliable than schematic, and of course, your eyes are the most reliable thing for determining which part is which. It is not uncommon for us during supporting customers for them to say, well, it's this memory part, and then we read it electronically and we see a different ID. We say, are you sure it's that memory part? They say, yeah, that's what the schematic says, but things change and the schematic does not always get updated. So I suspect most old hat engineers have already learned that lesson. I had to learn that lesson a while back, and I figure I can share that with some others. So now we have a resistor pack. It actually looks like 16:1, 16:2. It's the same model. From our perspective, we actually don't care about the resistance value as long as it's not really low. 4.7K and 1K are the same because we are a digital logic system. So if I click resistor network, I can choose resistor 16 bust, okay, and it automatically classified it as a pull down because it determined that pin 16 is connected to ground. So those are my resistors. Click next. Transparent devices. So during the slides, we mentioned that low impedance resistors should be marked with the 2-pin model. In this case, I have intentionally left my 33 ohm, 10 ohm, and 100 ohm resistors. I'm going to call those low impedance out of my resistor definitions so that I can model them here. By the way, I am using Shift Select to grab multiple. If I choose Select Model, I can use the filter to underscore pin to find the model that I want. Click OK, and it associates it. I do want to mention that in our library, there are generally two types of model naming conventions. There's our utility models that are meant for maybe multiple families, like this buffer 244. So that can be used for really any type of 244 buffer. But then we also have some models that match part numbers. So for example, these max parts. I do recommend, even though you may have a perfect part number match, try to click that view button, take a look before you commit to a model. So my next step is actually this U7. It's a 244 buffer. If I right click view schematic, let's take a look at it. Let's see, so it's the second entry there. Let's pull that up. Make that a little bit smaller. Okay, so there's my buffer. Oops. And I need a transparent model, so I click select model. I'm going to use one of those utility models, the 244 buffer model. Click view. So I have a buffer that connects pin 2 to 18, 4 to 16, 6 to 14, 8 to 12. So I can see that this model matches my pin out. I have two enables that are active low, 1 and 19, so I'm fixing those low. And actually, we just got a question of how to create a model if it doesn't exist in the library already. So let's say I have this device. I can right click, select model, click new. Let's give it a name, SN74LVC244. See, now I'm not using the utility model naming convention. Instead, I'm using the exact part number. The disadvantage of using the exact part number is, at least from our perspective, part numbers in bill of materials are not always perfect. Some companies may leave off the ADB. Some may also have like tape and reel information that we just don't care about that may make it harder to match. So I've specified a name. I choose directional if I need to. It looks like this is directional from A to Y. So click directional. That changes these to input and output instead of just pin and pin. And then I start typing. So pin 2 connects to pin 18. Pin 4, and let me zoom in on this a little bit just so that we can all see. Connects to 16. 6, 14. And by the way, this is a text file on the back end. So if you prefer just to edit the text file directly, that is perfectly fine. 7, 15, 5, and finally pin 17 to 3. And then I also have my output enables. So I want to fix low pins 1 and 19. separated with a comma. If I click OK, I now have this model. Click OK, and I associated my new model. So note that that model will be added to the library. So if you wanted to carry this library forward to another project, you can just copy that .lib file from this project to the next. And that's transparent. So this is our only transparent device outside of our resistors. So if I click next, let's see, what do we have here? So my boundary scan devices are actually out of order. U2, 3, 4, 5, and then 1. I know that it should be based on my block diagram. Let's go back to page 1. 1, 2, 3, 4, 5. Very simple. If you're not lucky and whoever made the schematics for you did not include a block diagram, how do you determine this? You probably want to search for TMS TCK, or you find your JTAG connector. So let's say on this it's P1. Let's find my P1 connector. Almost there. Of course, it's going to be the very last one. There it is. And then I can trace through this. I can determine that this TDI goes to my first device, which then goes to the next device, goes to the next device, and trace through. The software is going to do that with your netlist automatically. If I click this arrange button, it traces through, determines the order of the scan chain, and sorts it accordingly. If I click draw, I get a diagram showing the devices. So for example, R22 is part of my chain. It's a passive resistor that's there for termination. If I had more resistors here, it would be able to determine that those resistors are there to create connections. If I have a multi-tap system, like let's say I don't just have one tap, I can add tap breaks by clicking and dragging one of these in. And then that will specify where there's a break between tap 1 and tap 2. From our software's perspective, we are then going to essentially treat this as if the tap breaks weren't there, but we're going to use our JTAG hardware to connect them together. If you need to change the mode, put a device in bypass or something like that, we can do that here by clicking that little down arrow to get the drop-down menu. And if 1149.6 is available, we will tell you that here with that yes column, a yes in that column. Click next, and we are on to our last modeling step, which is memories and clusters. So first we have U8. This is an SSRAM, 32K by 32. Our memory model format is called MIF, M-I-F. If you have a support contract with us, memory models are part of your contract. We will create those for you. You just have to send an email to support@corellis.com with a part number, ideally also with a data sheet, especially if it's not something we can easily grab online. And we'll create the model for you. It's part of the contract that we have for support services. But if you want to use our built-in model library, you can select memory. It'll search the library, build a table, and then we can filter that table parametrically. So this is intended to somewhat resemble what you'd see on like a component distributor site. So I have a bill of materials that tells me, let's see what we have. I have MT58 L32 L32. It's IC, it's SSRAM, so I can start with type SSRAM. 32K by 32. So depth is 32K, width is 32, and that filtered me down to 2 models. One of those is in our default library. The other one is because I've used that model in a past project. It got copied to my automation configuration. If I click use selected, it adds that model, and that memory is now ready to be tested. For U9 and U10, I can either right click use select model for all, or I can shift select multiple if I want to associate a model with multiple parts. click select memory, click OK. Okay, this time I need to clear my filter, so reset filter, and then let's see what we have. SDRAM 4M. Apologize, I lost my interface over here. There it is, okay, good. And width is 16. So I still have a lot of options. I have a Fujitsu version, an ISSI version, a Micron version, and a Samsung version. So I know that this is a Micron part because I see that MT. I can also use part number search. So let's say MT48 LC4M. Whoops, LC4M. There we go. 16A2. So I have a lot of options for finding my memory models. Notice, let's clear that. Notice that we do have SDRAM 4M by 16 TSOP 54 package for 4 different vendors. These are probably meant to be compatible. They follow the same SDRAM standard that others follow so that it can be used in a PC or an embedded system. But what we find is when we operate these devices at low speed, when we are running our boundary scan tests, the Micron part and the Samsung part are not fully compatible. They will behave differently when we turn off their DLL, when we operate them at low speed, meaning that we need a different model for each. Now, sometimes they're the same. We can use the same model for Micron and Samsung. In fact, if you come to us and we have a model for Micron, you come to us with a Samsung part, usually our first step is try the Samsung model on the Micron part or vice versa. But otherwise, that is a point that I wanted to make. Unfortunately, when we operate these at low speed, some of these devices will behave differently than we expect, and we do have to tweak our models accordingly. If our support group does give you a model, you can just click Browse for MIF and grab it. But in this case, I am going to use this model right here, Micron MT48 LC4M16A2. Click Use Selected, and it loads it. Notice that these are the same part. If I right-click View Schematic, we can take a look at them and how they're connected. So in this case, we have our control bus is connected in parallel. So you can see that SDRAM address 11, SDRAM address 11 down to 0. These are all connected to both of these parts, U9 and U10, but they have an independent data bus. So data 0 to 15, and then data 16 to 31. This is a bank of memory. So this, from the system perspective, it's like one big 32-bit part. And that means we can operate them at the same time by choosing auto bank memory. So if we right click, choose auto bank memory, it specifies them as a bank. So that means instead of testing these individually, it will now test them as a bank. It will run the test on both of them at the same time. For Flash, it's a different modeling system. It's called the DEV model, DEV for device model. So I click Select Flash. It does pattern matching to compare the bill of materials part number to our model library. If you have older NOR Flash, and I think even some modern parallel NOR Flash, they're configurable either as 8-bit or 16-bit. So we do need to choose the appropriate model. In this case, it's configured as 16-bit. So we use the word model, right? A word being 2 bytes. If it was an 8-bit device operation, we would choose the byte model. So we choose word, the appropriate package, FPGA. If you want to compare the model against your schematic, you can click View Model, or sorry, View Model Information. Some of these options I will be going over when we get to in-system programming, and then design for testability in system programming optimization. So for now, I'm just going to specify the model. I don't need a custom device file, I need a data file. So I go browse to data file, I'm going to grab my data file from my example files, click OK. It says you haven't turned on erase program and verify. Would you like to do so? I say yes, I do. Click OK. And I now have a model and a data file for that flash device. U12, we're going to repeat the process, select flash, pattern matching found 28F160B3B, and pick the right type for me. Data file is scan plus DB U12. Click add. Yes, I want to enable erase program and verify. Click OK. And there we have it. One more device to model. This is our very last device. Let's take a look at what it is. So we right click view schematic. It is an oscillator. So this is a 50 megahertz oscillator. Output enable goes to power. That is being pulled up. That's an active high signal. So this will always be active. What does that mean to us? It means that pin 3 is going to be oscillating at 50 megahertz at all times. If this pin over here, pin H17, is a boundary scan pin, we don't want to accidentally drive this pin while the clock is also driving. That's contention. That means that when that clock goes to the opposite state of what we have here, we are going to have more current than we'd like flowing because they are going to be at opposite values. They're going to be contending. One's going to be trying to drive high, one trying to drive low. So to avoid that, we can use a SIF model. I can go to select cluster. Oh, nope, never mind. Disable cluster, sorry about that. And this model format has not been moved to a search format, so we still need to browse to files. So if I go to Corellis, ScanExpress TPG, cluster information files, I can find the oscillator 4-pin. I'm going to open that in my editor just to show you as I select it. So this is an older model, and it's a very simple format. It says, let's pull up the schematic so we can walk through it. Pin 1, when low, disables pin 3. So in other words, if this is low, it's telling the software, then this pin 3 will be disabled, and that means that we can freely change the H17 value. And it's saying pin 3 is an output. Very simple model format. This is meant for disabling non-boundary scan devices. You can come up with a similar effect just by doing exclude net PowerPC sysclock R right here and constraining output enable to the right state. But of course, we don't need to add a constraint because it's strapped to 3.3 volts. And that was our last model. This board is designed to be relatively easy to generate a test procedure for and also show how boundary scan can work. In a real project, you're probably gonna have more than 14 U numbers. So it may take a little bit more time. I am now at constraints. So first of all, I can change my coverage level. If I'm debugging or having problems, maybe I want to switch my coverage to partial, which means we are only going to test nets that have just boundary scan device pins on them. I can then bump it up to modeled, which means boundary scan device pins and any devices I've added models for. Moderate then adds single pin nets, it adds all pins except for single pin nets, and a single pin net in this case meaning a pin that has only one boundary scan pin. So if you have two boundary scan pins, then it will include that. If it's only one boundary scan pin, it will not be included. And finally, all possible boundary scan nets is complete, and extensive would be also adding additional vectors to the bus wire test. Scope can be applied globally or to each individual test step. And let's go ahead and change this to complete, click add. And let's see, what do I need? I have, well, first of all, the most relevant filters looking for certain patterns like chip enable, CE, output enable, OE, reset, program. So it's looking for certain terms that we associate most with constraints. So in this case, I have program N for my Xilinx Spartan 3. Right click, view schematic, and let's take a look at what that does. So here we have program N and init N. Program N needs to be pulled high, init N needs to be pulled low. So I can either fix it high or use, because I have that pull up, I can use sense high. Click add, it adds it to my constraint list. Init is the next one. That one I need to be low. So sense low, click add. You can add comments. So for example, program N high to prevent configuration on what U number was that? U2. And then init N low to prevent. So it's a good practice to keep add comments to your constraints so that either yourself or somebody else continuing development on a project will remember why something was constrained. Click next. We're now finished and ready to generate our tests. So we've got infrastructure, interconnect, bus wire, pull up, pull down, memory, and flash type test steps. When I click finish, it's going to ask me, do I want to add my new part number mapping to my library? Yes, I do. Click yes, and we are at the generation phase. So we have 1, 2, 3, 4, 5, 6, 7, 8 tests ready to be generated. You can change the order by dragging and dropping. I personally prefer numerical order, so I put U8 before U9 and U10. This is our preferred order of execution as well. Infrastructure test is going to test to make sure your scan chain basics are working. Interconnect is going to start looking for open and short faults, but the patterns are going to drive in a single direction. And I'll try to explain that a little later. Buswire test is going to drive in multiple directions. Resistor test for those pull up and pull down, and then memory test and flash test is going to be testing your volatile and non-volatile memory peripherals. If I click generate all here, click yes, it generates my tests. Green means good. Green means that it was able to generate it and that there were testable portions of it. If, for example, I go back to preparation, memories and constraints, change partial coverage, next. So the definition of partial is only nets that have only boundary scan will be included in interconnect type testing. So what does that mean for the resistor test? Well, the resistors are not boundary scan devices. They will be excluded. Now cluster type testing will still be included, but the resistor test will not. So I'm going to go back, change that back to complete. Some experience with this. So if I generate these tests, everything passed. If I look at the test step generation status, let's pull that magnifier back up because this is a lot of text. It's going to tell me information about the generation. So in this case, my infrastructure test generated successfully. It wrote out a CVF type file to my documents, Corellis TPG projects folder. Completed with no errors. If we look at some of the others, so let's say interconnect test, we have one warning here. So it is warning that my compliance enabled net program N contains boundary scan output pins. So what does that mean? Let's turn off the magnifier. In this case, I do have a boundary scan output pin connected to program N. I could assert program N, cause this FPGA to go into its programming mode, configuration mode, and cause all of my tests to fail because it's no longer in boundary scan test mode. So this is warning me about that. Now I've handled that by telling the software do not drive this, instead just sense it high. So one of the most common cases for tests not working the first time is a missed constraint. When you maybe have a compliance enable, a reset signal that you wiggle during the test that causes a device to reset. Things like that can cause significant failures. The system will just stop working. You'll notice that for flash test steps, we will attempt to optimize the scan chain, meaning if we can change a device's mode to clamp, high Z, or bypass, all of which connect us to that 1-bit bypass register, we will attempt to do that. So here we can see boundary scan device modes. U1 is going to be in clamp, U4 is in clamp. We are only going to put U2, U3, and U5 in X-test mode during flash programming operations. And I mentioned earlier, every single one of these files is human readable. So I can open up the netlist, I can read it. I mentioned earlier, at Corellis at least, we like to use the netlist as our debugging tool, often in place of the schematic. For example, I can see that flash address has pins from U3, U4, U11, and U12 on it, and that can lead me to issues or resolutions to issues of maybe the software thought things were connected when they shouldn't have been. Topology file. So chain 1, devices, U1 through U5, all in mode X test, and the BSDLs that they reference. Again, if you like to edit text files instead of using the graphical user interface, feel free. This is meant to be edited. So here we have include all, which is specifying our test coverage level. We have the constraints that I added. We have the comments that I made. So in this case, the comments got copied here, and it'll work the other way around too. If you add a comment before a constraint, it'll add that to your comments. We have these disable commands. These were generated based on the models that I associated. What these are saying is when it is not testing U10, disable U10 using information from the memory information file. That tells the software, for example, constrain output enable to the deasserted state so that it's not outputting. If you want to add another test step, so let's say I want to create another interconnect test. I can go test steps, add new test step, or my favorite way to do it is right click, duplicate, and we'll call it interconnect 2. And you can see we have different test step types that you can select based on the radio button. If you were adding a script test step, I could click that here to specify that. But for now, I'm adding another interconnect test. So let's say I want to run a second interconnect test, but I want a special topology. So I'm going to double click my topology, file, save as, and let's call this U5 bypass. Now, why did I call it that? My text editor added .txt at the end. Sorry about that. .bsdl, no, .top. There we go. I am going to change the mode of U5 to bypass. Click save, close it, and then generate. So I now have 2 interconnect tests, one for all of my boundary scan devices, one with U5 and bypass. So let's say that U5 could act as a buffer. Maybe I want to test U5's functionality by testing through it with my interconnect test. I could do that. I could add a model for U5 to be a buffer or whatever its functional behavior is. We program U5 to be a decoder, and then we bypass U5. So a device that is bypassed, hopefully you recall from this morning, a bypass device is in mission or functional mode. So in mission mode, the device does whatever it does. In this case, it's programmed to be a decoder, so it would do that. So the next step, it's flashing right here. And let's see what we've got. So I'm going to make sure I have no fault switches. No fault switches. I'm going to open up runner. Let me get rid of that interconnect too. I don't want to run that right now. Set up my controller. Let me run this once more, but with this photo up. Can you see those LEDs changing? That's actually the address pins counting up as we are programming the flash device. Those LEDs are connected directly to the flash address pins. So you can see we are currently programming flash. As we access different locations, those LEDs are illuminating and counting up. Now we're programming U12, again using the same address bus. And finally, we're done. So that's our test run on the ScanPlus demo board. Thanks for watching. For more information, visit our website at corellis.com.